Then welcome everyone to the second lecture on requirements engineering. Today we are going to talk about elementary core activities in requirements engineering and core principles, among them the refinement of requirements over different levels of abstraction. And with that, we are going to close the basic chapter on the fundamentals before the next week and the next lecture, starting with the engineering approaches and discussing requirements engineering in context of these engineering approaches. Now, before starting, let's recapitulate the previous lecture. So in the last lecture, you learned many things, I hope. Among them, 4 key essential takeaways. Number 1 being that requirements engineering is not a means in itself, but a means to an end. We discussed that many approaches that are available out there tend to be written in a slightly apodictic manner without explaining under which conditions to use that approach, what the benefits are, what the weaknesses are. In the very end, what counts is whatever serves the purpose. So the ultimate goal of requirements engineering is always to create a requirement specification that is agreed upon all stakeholders. And in the very end, what counts is that the requirements we write, that they fulfill a specific purpose and accommodate the surrounding software development process. The second thing we discussed is that requirements engineering is not just about software, but also about humans, systems, and processes. So in this course, we will be focusing on requirements engineering for software-intensive systems. Nevertheless, we will also have to accommodate, of course, the humans and everything surrounding those software systems. Never forget, software is built by humans for humans, and especially requirements engineering is largely about mediating between all the different stakeholders that have a specific interest in the software system under consideration. Third, collecting all requirements and specifying them in an unambiguous manner upfront is an illusion. Remember when we discussed the definition of requirements engineering and the elementary tasks, among them elicitation, that we said that one of the goals is to elicit all relevant requirements and not all requirements. Collecting all requirements, identifying all requirements is something that we consider to be not really possible, but also not really useful. Otherwise, we would, even for a simple web shop, have requirement specifications that would be several thousand pages long. Last but not least, requirements engineering can have different forms and interpretations. What we discussed is that there are many different requirements engineering approaches out there, and regardless how these are shaped, they all share certain commonalities, and among them are the core activities in requirements engineering and selected principles in requirements engineering, which affect the way we structure the levels of abstraction and how we refine requirements over these levels of abstraction. And this is what is in scope of today's lecture. Now, what are the goals for today? So we will be refining the terminology a little bit further, and we'll be discussing different requirements, classes, and categories, and how these requirements are refined and how we can classify them, sometimes only by refining them. We will be very briefly only discuss the core activities and requirements engineering, and then largely focus on the levels of abstraction in software and systems engineering, but of course with a particular focus on requirements engineering. And this shall, as I said, conclude the fundamentals and lay the foundation for the third lecture, where we will be discussing requirements engineering in context of software processes, and lay the foundation for the MDIA approach, which we will be using along the remainder of the course. Now, the outline for today, we'll be talking about 4 major topics: requirements, classes, and categories, and refinement of requirements of different classes. We will be very briefly discuss elementary core activities in requirements engineering, and then focus on the levels of abstraction, which we discussed very briefly in the last lecture in context of the problem space and the solution space. And then we will conclude with a final discussion on challenges in practice, which we were not able to discuss in the last lecture because there was still a little bit of a gap concerning the refinement of requirements. So let's directly start with requirements, classes, and categories. As discussed in the last lecture, a requirement is a need or constraint imposed by a stakeholder. So taking the stakeholder perspective, and a capability, a property that a system shall have. So taking more the system perspective in order to accommodate these needs of a stakeholder. And of course, the documented representation of a need, capability, or property. We will be refining this definition in a second when we talk about the requirements classes. What we also discussed is that requirements engineering is a means to an end, which means that the ultimate goal of requirements engineering, namely the creation of a requirement specification or the elicitation, identification, and specification of requirements, they need to fulfill a specific purpose. And this purpose can be quite manifold, depending on the surrounding software process. We need requirements to communicate with the stakeholders, of course, among many things, but over and above all, to communicate their desires, their needs, the expectations, the problems we intend to solve in engineering. We use requirements, of course, from the perspective of engineering itself, from the solution design to design, implement, and then also test and integrate a software product. And of course, we need also requirements for different project organization and management techniques, ranging from the elaboration of contracts. So very often requirements form a specific aspect of a contract, over effort estimation. We use requirements to estimate the effort necessary to implement those requirements. Think of planning poker, just to give you one example, or risk management. We use requirements to assess potential risks that come along these requirements. Now, in order to do this, requirements need to be of high quality, whatever we mean by high quality. Remember the first lecture when I showed you the picture of the beers? I assume that you will remember this picture. I'm not sure if you remember what I said along this picture, but we compared this with beers and said that same as with beers, the way we do this, so the way we create the requirements, specifications, is also to a certain extent a matter of the organizational culture. At the same time, we need to respect certain ground rules. For brewing beer, it is, it should be, at least from our perspective, the German purity law, that tries to define a certain threshold or a quality standard. And we have the same, of course, for the specification of requirements. Now, what would you say is a specific characteristic for a requirement that is of good quality? So how should a requirement in principle be? What do you think?
I think it should be unambiguous. It should have one meaning.
Very, very good. Yes. Unambiguous. What does it allow if a requirement is unambiguous? If it has only one meaning? Why?
So you don't have like multiple requirements in one requirement. So it's easier to check, have I fulfilled this requirement?
Exactly. You're touching upon many, many topics that we are discussing now in a second, that allows for an unambiguous interpretation and design, and that it's also testable so that we can objectively decide if a software system fulfills that requirement or not. So there are many quality criteria out there. We will be discussing these quality criteria and the quality models we can use for a quality assurance in the respective lecture towards the end of the course. So, but for now, I would like to increase your awareness for selected quality criteria, which we will be using in today's lecture. Now, one standard that defines quality and also quality assurance techniques, also in context of requirements engineering, is driven by the IEEE Association. And this standard defines characteristics for individual requirements, so what every single requirement should fulfill, but also characteristics for larger sets of requirements. For example, the whole requirements specification. Among them, the completeness, a requirement specification should always be complete and it should be consistent, so that the requirement should not make contradictory statements, for example. Just one note on the completeness. As I said earlier, there's no such thing as a completeness. It's impossible, even the standard says it, it's impossible to ensure the completeness. Nevertheless, we can achieve a sufficient completeness by focusing on at least the relevant requirements. As for quality characteristics of individual requirements, we have the correctness, the feasibility, the unambiguity, as you mentioned, and the verifiability. So correctness means that the requirement really reflects the need of a stakeholder, that the requirement exclusively reflects the need of a stakeholder. But again, also here, same as with the completeness, we cannot really ensure that a requirement is really correct, at least not if considering from a, like a mathematical proof, but we can approximate a sufficient correctness, and we have many different means and techniques. Also, for example, creativity techniques in our disposal that we can use. Feasibility means that that we are able to implement a requirement eventually. So typically we focus on technical feasibility, that it's technically possible to implement the requirement. But there's a little bit more to this. Feasibility also quite often refers to a cost-benefit thinking. For example, the availability. Imagine a system where the stakeholder says that this system should be available 24/7, 100%. It might be technically possible, but it's also a question whether the effort to implement this and the operation cost justifies the actual value of a 24/7 availability. Another aspect of feasibility relates a little bit to the consistency. So there are also some cross-cutting dependencies between the different quality criteria. Some requirements tend to restrict the possibilities for other requirements. So, for example, think of security. So the higher the security needs, the higher the chances that they will have some problems with usability needs or accessibility needs. Think of an application. Imagine that you would have to authenticate with every single step or every single function that you call. You would, every time that you need to authenticate, that you need to call a function, you would need to authenticate. This is, by the way, if I may add, exactly how LADOC has been defined. Every time we do something, we need to log in again and again and again. And you can imagine that usability goes down. So this, all these thoughts play very well into the discussion around the feasibility of a requirement. Unambiguity, this is exactly what we discussed right now. Are we able to objectively decide if what the requirement really means and if a system fulfills that requirement? And verifiability means, are we able to objectively test the requirement, or more precisely, test a software system against this requirement to check if the software system fulfills, or a function in a software system eventually fulfills a requirement. A last remark on this: the verifiability is always a very good indicator to see if we need a further refinement of a requirement. So if a requirement is not verifiable, chances are that we need to further analyze the requirement and further refine the requirement. Now, one thing that is related to these quality properties is that a requirement has always a form and a content. So we distinguish form and content. The form is the syntax of a requirement. It describes the way this requirement is specified. We can do this with natural language, typically structured in very large, like spreadsheets. We can use figures, we can use models, for example, the Unified Modeling Language, we can use mathematical models, and so on and so forth. And so there are a multitude of options to specify a requirement. And of course, the content, so the semantics, the meaning of the requirement, the assertions we actually make with the requirement. And both have a strong influence on the different quality criteria. Now, there are some people out there who, how to put this delicately, there are some people out there who have some good arguments for that, to use, for example, mathematical models to specify requirement specifications using formal methods, for example, temporal logic. And the argument is that these requirements are very, very precise. And this is true. As it said, how is the saying? Outside mathematics, there is no certainty, which means that only mathematics allows for absolute certainty. Now, this is true. These requirements tend to be then very precisely formulated, and they are definitely verifiable. Now, but two things. even if I use a very rich syntax with a high expressiveness and mathematical rigor, this does first not mean that the content is still right. So the requirement could still be wrong. And this can very negatively affect the understandability of a requirement. Always keep in mind that people need to read and understand the requirement specifications. And among those people are, of course, the customer side stakeholders. And in most of the cases, they cannot really interpret mathematical models, which is the reason why the majority of the requirement specifications, and we'll put also focus on our course on this, are written in natural language. There are ways to increase the precision of these requirement specifications written in natural language, but in the end, it still is natural language free text that we use structured in tables, but still free text. Now, let's talk about requirements classes. The easiest way of distinguishing different requirements classes, and this is also the most common way, is to distinguish between functional requirements and non-functional requirements. So functional requirements are requirements that describe user-visible behavior of a software system. So all the functions or functionality that a software system shall provide. So think of Google, a functional requirement could be that if I enter a search string, I want to see a response with all the relevant websites that I'm searching for. So functional requirements describe the user-visible, external, as we say, user-visible software behavior. Non-functional requirements, simply speaking, is everything that is not functional. Now, why even bother, before we go further, why even bother with distinguishing between different requirements classes? So why is it important? So the category of a requirement very much influences the way we handle the requirement, or the other way around. The way we work, the way of working, puts emphasis on a specific class of requirement. And this is very much true. We elicit functional requirements very differently from non-functional requirements. We refine them very differently. We specify them very differently, and we measure them very differently. So the test cases we employ tend to be very differently for functional requirements and for non-functional requirements. Typically, functional requirements are in scope, at least to outline the basic functionality of a software system. Non-functional requirement is very often something that tends to be at the very end and retrofitted. This is a problem. Think of the same example we discussed in the first lecture of Google again. The search query might be giving correct results, so the functionality might be fulfilled. But if you have to wait 2 or 3 minutes for every query you make, the system is not usable. So it's imperative to also watch for non-functional requirements. Now, what are non-functional requirements? We are having a dedicated lecture on non-functional requirements, but in the end, also here we can distinguish again different requirements classes, and we will do this in our course. We distinguish system-specific quality requirements, so quality properties that a software system shall have. Here we are talking about things like performance, usability, maintainability, security, safety, portability. The list is very long. Very often they are called the ILITs because the standards define the different quality criteria as such, like maintainability, portability. I don't know, the list is really long. And what we call process requirements, the second category. So process requirements can again be 2 different things. One class of process requirements are requirements towards the development process. Here we take a more management perspective on, for example, scheduling, milestones, budgets, risk plans, risk lists, typically in requirements engineering, and all these things that affect the general way of working and how we do so, where we, for example, define specific milestones, where we say the requirement specification needs to be created until a specific date. It needs to be quality assured following a specific standard, and so on and so forth. And the other thing are definitions and rules for the actual implementation called constraints. Now, constraints are, although we focus only in the problem space, constraints are the only way for us to restrict the solution space upfront, where we can say that certain technologies, for example, have to be introduced that we need to use, for example, a specific infrastructure, that we, for example, must not use specific programming languages or paradigms. For example, that object orientation might be excluded, that we are not allowed to use Java because we have specific demands on safety critical systems, things like this. Now, there are a couple of more terms and related concepts which we will discuss now. One of them being a requirements engineering artifact. I'm using the term artifact all the time. Let's now finally discuss what an artifact is. We are giving a proper definition in the next lecture when we are introducing the MDIA model. But for now, an artifact is the documented form of one or multiple requirements, for example, a requirement specification. So the artifact is an outcome of our activities. Whenever I create something like a list of requirements, a list of non-functional requirements, a list of constraints or context information, then we are creating an artifact. Now, one thing to take away already now is that the requirement specification or an artifact, more generally speaking, doesn't have to be a document, doesn't have to be a Word document, doesn't even have to be a document at all. It can be a spreadsheet, it can be an entry in a database. I think one of the most commonly used tools are still DOORS, which is essentially still just a very expensive spreadsheet, but it can be anything. It can be an issue and so on and so forth. Now, another term related and important here is the one of a stakeholder. Now, stakeholders are individuals or groups of individuals or institutions that have a specific interest in the system under consideration. So typically when we talk about stakeholders, we mean human beings, so customer side stakeholders, but it can be also institutions, for example, a regulatory body. And related to that is one thing that you need to understand. Interest in a system does not mean interest in the success of a system. So think of the workers' union. The job of the workers' union is to ensure that certain regulations are upheld, which means that if a system goes live or not is not really interesting to them. What is interesting is that if we have a system, that it preserves whatever is agreed within this regulatory body. There are certain domains where the regulatory body is very strong. Anything that is related to the development of safety critical systems, for example, and the avionics field or the automotive sector, but also anything related, for example, to finance, the banking sector or the healthcare sector. So, and these stakeholders are very, very critical for the success, or accommodating the needs and the restrictions imposed by those stakeholders is very critical for the success of a development project. Now, another term that is important is the one of a rationale. So the rationale explains and justifies a requirement. I tend to say that a requirement without a rationale is a cost-intensive assumption. So every requirement needs to have a rationale. The rationale is what we specify to answer our why question. Think back of the why and the what and the how. We will be using this analogy again in a second, but the rationale is what explains and justifies the requirement. And finally, a requirement source. When we elicit requirements, we make use of different requirement sources. This describes an aspect of the real world from which we can elicit requirements, from which requirements originate. It's also very much related to the rationale. So a requirement source can be a law, a norm, standard, or compliance rules. In this case, the rationale is quite easy to specify. It can be any stakeholder. Think of requirements elicitation workshops where I interview the customers, the end users, and then the requirement source that I would document would be, for example, the transcript of this interview. And the list is very, very long, much longer than what you can see here. We will be discussing this when talking about requirements elicitation in the fourth lecture. Now, one thing that you can maybe assume already by this is that a requirement specification is not only about listing the most relevant requirements. So what we specify in requirements engineering is actually twofold. Number one, it's the requirements, of course, first and foremost, that define the properties and capabilities of the desired system. But it's also a lot of context information. A requirement specification should always be self-contained, at least to a certain extent. And the context information is necessary to provide the understanding surrounding the software system. So what is part of the context information? It can be anything. It can be domain knowledge. It can be the terminology associated with domain. For example, think of a healthcare system, like, I don't know, a medical device. Don't assume that developers are very familiar with the domain. So we need very often rich descriptions of very basic terms to this domain. It can be data models, system boundaries, when we draw our context diagram that defines what are the interfaces of a software system, how do we interact with these interfaces, graphical user interfaces, for example. It can be also immutable rules, constraints, laws, also the laws of physics. Think, for example, of a satellite system. At some point, you will shoot that satellite system into the orbit, and the higher this satellite flies, the more we have changes, for example, in the pressure and the atmospheric pressure, things like this. And these things typically have to be specified very, very precisely. So the more complicated a software system becomes, the more important becomes the context information. Now, last but not least, liability of requirements. One thing we will be discussing at the very last lecture when we talk about requirements management is that a requirement can have a different status or a status model, an underlying one. And this very idea of such a status model is that it should always reflect the life cycle of a requirement. Now, a requirement can be seen as an initial candidate. So, for example, after an elicitation workshop, it can be just an assumption. Imagine that you have a bunch of requirements and that you just see, even as a designer, there is some information missing. So I just assume that there's another requirement. Or it can be an actual requirement, as we say, that has been formally accepted by a stakeholder. Now, one of the core tasks and requirements engineering is to identify these assumptions and candidates, elicit them, refine them, classify them, prioritize them, and so on and so forth, to make them concrete, tangible, and usable, and especially formally accepted requirements. And the clearer a requirement becomes, the more it becomes measurable, testable with this, but also the higher the chances of actually understanding the requirement, understanding the true purpose of the requirement, and of separating, as we say, actual requirements from wishful thinking. Now, I would like to give you a very small example for the need, or to highlight the need of these different tasks. And I would like you to put some thoughts into this and take a little bit of time to think about this. Now, on the left side, you can see a pictogram of an ATM, an automated teller machine. It's in bank automata. And we will be using this example along the whole course, simply because everyone should know this. So I know that we are in Sweden and that cash is not really a thing here, but there are some countries where we still love to have cash in our hands. So we are still using this example. I just assume that everyone knows what I mean. Now, imagine that you are in a workshop, and then one of the workshop's participants says, the system shall be secure. So this is one of your requirements candidates. Now, the question is the following. What is it? The system shall be secure. Is it a functional requirement? Is it a quality requirement? Is it maybe a process requirement? Keep in mind, it can be anything related to the actual way of working, or a constraint, or is it neither of the options? Now, I would like you to just put some thoughts into this. Take 2 minutes time and think about this. I will turn off my camera and mute myself, and I will come back in 2 minutes. Take the time, it's worth it. Good. So, what do you think? Is it a functional requirement, a quality requirement, a process requirement, including also constraints, or is it neither of the options? I see. Yeah, I know. I see you struggling. I'm struggling myself a little bit. Correct. At this stage, so in order to be able to classify requirements, always ask yourself the following question. Can I objectively demonstrate that the system fulfills the requirement? Is the requirement verifiable? In this case, it's not. Exactly as you said, it can be anything. It could be an authentication mechanism with a PIN code, for example. It can be anything else. It can be also that the system is not, I could install it in a basement, nobody can access it, it's secure. But it's not maybe what the customer really intends with the system. In this case, it's neither of the options, and at the same time, all of them. So it's not really usable. And, oh, sorry. And one of the elementary tasks of requirements engineering is that requirements have to be engineered. And this is also the reason why we still say requirements engineering and not, for example, agile requirements or whatever. We focus very much the engineering part. Requirements are typically very vague and very ambiguous, and they tend to be not measurable at all when we get them at first. And it's elementary in requirements engineering to continuously engineer them by refining them and classifying them, as you suggested, specifying them and validating them. Now, let's take this example and put this into context. In the first lecture, we discussed generally the problem space and the solution space. And we said that in requirements engineering, a focus on the specification of the problem space. And we highlighted some exemplary questions related to the problem space and the solution space. In requirements engineering, we tend to answer two questions. Number one is why is something necessary? Number two is what exactly is necessary. In both cases, I take a black box, what I call black box view on the software system, which means that I don't really care about the internal realization of the software system, but just from my user visible perspective, what the system or what kind of functionality the system shall provide. And in the solution space, I take a glass box view where I provide some information or specify how the software system should be internally structured, how the behavior should be realized. Now, let's take this very example, the software system or the system shall be secure. This is a perfect example for a quality goal. It's high level, it's not measurable, but it justifies, it's a good rationale for subsequent requirements. Now, and requirements themselves, I can specify again over different stages of refinement. I can start with some coarse-grained requirements that I tend not to document. Of course, the thing that really matters is the outcome, the precise, the fine-grained requirements. But a coarse-grained requirement describes general properties and characteristics of the system that are useful for further work, for further refinement, but maybe not really measurable. So one example for security could be that the system shall prevent unauthorized access. Now, and this I can refine, of course, further to the level of what we call atomic requirements that are unambiguous, objective, where I can really define, can provide a yes-no answer to whether my system really fulfills that requirement or not. And an example for such a requirement could be that I need to authenticate using my PIN code. Now, two things. Number one, as I said already, this is still a black box view. I still specify my requirements from a user visible perspective. And number two, during this refinement and classification using this PIN code example, what I did is I refined this quality related goal to a functional requirement. So this is also a key takeaway that during the refinement over different levels of abstraction, the requirements classes tend to change back and forth, back and forth. This really doesn't matter for us. Very often we tend to focus on functional requirements because this makes our life easier. But in the very end, what counts is that I can refine them to something measurable and decidable. Now, what you can see here is, again, another example, just but over these different levels of abstraction. Ideally, or in an ideal world, we do this always top down because we think of a greenfield engineering where I start really from scratch. doing my, for example, elicitation workshops, I identify very generically phrased goals, like the system shall be secure, or like here, the product must be usable in an international setting. And this I can then further refine over different levels of abstraction, for example, to coarse-grained requirements, where I can say, for example, the product must be usable in developing countries, where I have, for example, some issues in my power supply or some issues in my digital infrastructure. Think of Germany, for example, and infer requirements that the product must be resistant to issues in the power supply. And this, again, I can refine further and further until I reach a level that is really decidable. For example, and here I have taken intentionally some examples that are not really functional requirements, but just that you see also the process related side, where I can say the system needs to have an independent emergency power generator. This is more a technical constraint where I just say we need this kind of infrastructure. It doesn't really affect the actual functionality of a software system. And you can do the same on the solution space side, where you can say for the generator, we will contract a specific company, for example, or we will deploy a specific already existing solution. A final note, of course, also the other way around is also possible, very often phrased as reverse engineering, but truth is that we are always somewhere between both. It's always a continuous top-down and bottom-up, and this we will see also in a second. Now, before continuing to talk about the different levels of abstraction and the notion of requirements refinement, let's talk about the elementary core activities in requirements engineering. Now, in the last lecture, I introduced the very basic tasks in requirements engineering, ranging from elicitation over analysis and specification or documentation up to validation and verification. Now, what you can see here is the so-called Reckman process framework that has been developed by Jörg Dörr from the Fraunhofer Institute, that specifies those core activities in more detail, including these elementary tasks like the elicitation, analysis, specification, and V&V, validation and verification. Just to recap, validation focuses on the quality assurance of the requirements themselves, meaning are we building the correct system? Verification means ensuring that we build the system correctly, refers typically to things like testing, for example. And on top of that, we see related requirements management activities. Now you see also color coding. Blue denotes those activities that are seen as core activities, which means that this is the least common denominator across all the different approaches. White denotes supporting activities, those that need attention only in special cases, for example, in dependency to the application domain. So for example, when it comes to the requirements elicitation, no matter how we work, we will always be concerned with identifying the requirement sources, identifying the stakeholders, defining their goals, a lot of scoping, but only in some of the cases we are concerned with analyzing business process models. So this could be the case, for example, for the banking sector, finance, where we typically are driven by business process models. In other cases, think of the automotive sector, we don't have business processes. Or think of embedded reactive systems, we don't have these. Very much the same holds for validation and verification. In some cases, we might go for formal verification. In other cases, we go for the specification of test cases. So I won't go too deep into this because we will be having a dedicated course related to all these aspects of verification. Now, as I said also earlier, that in this course, we will be taking a process agnostic view. So we'll be putting a lot of attention on the actual artifacts, on what the outcomes of requirements engineering is, and less on how we work. So what are the detailed processes, so step 1, step 2, step 3, step 4, simply because this is not possible. I explained already that the exact approach to requirements engineering depends very much on different factors, rendering the way of working something very unique. Okay, this is not really comparable across all the different situations, which are characterized by differing surrounding process models, or affecting the way of working in general, but also how requirements are elicited, how requirements should be analyzed, how requirements should be documented, the family of system, and so on and so forth. Now, we will be abstracting from this and focusing on the artifacts, as I said, and taking this more process agnostic view. Nevertheless, there is, as I mentioned also earlier, one cross-cutting concern that is really regardless of the surrounding process model, and this is that requirements engineering always concentrates on elaborating a clear understanding of the problem space. So again, we focus on the context and the domain, which answers my why question, including all the goals that the stakeholders might have, and we focus on the what question, which means the actual requirements. Now, on the right side, you see a highly sophisticated model that I draw in PowerPoint, and we will be using this model now in the following to discuss this problem space and the solution space and how we jump back and forth a little bit in more detail. Now, when we say that in requirements engineering, we focus on specifying the problem space by identifying the why and the what do we mean by that? Now, this is just a pictogram that you can see on the right side. I hope that you can see my cursor. And this identifies the different entities that you specify in the course of elaborating the problem space. So typically what I do to answer my why question is I identify all these entities that surround my system. So think again of the ATM example. So in case of an ATM example, I might think first of who the stakeholders are. So one of them is of course my end user, the one that uses this ATM. Another one could be a clerk in the bank. Another one could be a regulatory body. The banking sector is full of regulatory bodies. But I have also many surrounding systems. For example, digital services and external systems that allow my ATM to check my balance, my current balance. I could also have some physical devices such as cameras, or maybe some, I don't know, fingerprint IDs, or the physical devices that allow me to enter, to add my debit card, and so on and so forth. So I identify my stakeholders and my external systems, and I collect all the relevant information, I should say all the relevant information available on the goals and the constraints. Okay, so one goal could be, for example, that the system should be secure. Now, once I have identified all this context that allows me to draw actually a context of the system, what is part of my system and what is part of other systems, so which features should be part of other systems, here comes scoping into play. I start elaborating answers to the what question. So what is really needed? And this is what is symbolized by these small arrows. So when I talk about functional requirements, as I said earlier, what I mean is that I specify user visible external behavior of a software system. What I mean by that is that I specify how I, as a future user of the software system, intend to use this system. So, for example, in order to authenticate myself, I intend to be adding my debit card and enter the PIN. And this is what we will see or learn in the lecture on functional requirements as one form of specifying functional requirements by interaction scenarios, by just describing how I intend to use the software system. Another way could be that I want to use a fingerprint. Another way could be that I want to authenticate contactless with my mobile phone, for example. But all these forms still capture a user visible view on the system without putting any care into how this system is internally structured. Now, this internal glass box perspective is what I take when considering the solution space. So here colored in blue. During the design and implementation activities, this is exactly the point where I start structuring my system. I can decide about which component does what. So which component, for example, is relevant for checking the authentication mechanism, which component is, for example, responsible for communicating with external digital services or other systems, for example, to check the identity of the user, and so on and so forth. So problem space, external black box view on the system. I identify my why. So who is interacting with the system and why, what are the intentions, and then what are the actual needs towards those systems And the solution space is the internal realization of these software systems, giving structure and behavior to these software systems. Now, there are other tasks when dealing with the solution space, tracing, verification, just to give you one example, of course, but also change management activities, or in general more project management activities. This is for now, for us, not really of any relevance. Now, when talking about problem space and solution space, I need also to talk about the artifacts, because there is some place where I need to document my requirements. And this is what you can typically find in practice. So the problem space is typically captured by the requirement specification. There are many different terms for that. Software requirement specification is the most commonly used one, and the solution space typically captured in the overall system specification. Also, please keep in mind that it doesn't always have to be one artifact or just one document. It can be multiple documents. In MDIA itself, we are actually relying on multiple documents. We are using two artifacts. One is for the context layer, for the why questions, and the other one is for the requirements layer, for the what question. I'm showing you this in a couple of slides, how this more or less looks like. In any case, the problem-oriented view tends to provide the answers to the why questions, so the goals and the strategies, but also the what, of course, the requirements, and any further related information that is necessary to use this requirement specification as a self-contained thing. Same, of course, holds on the other side, taking more this solution-oriented perspective. Now, a final thing for which I would like to increase your awareness is the following. So when we work on the problem space and the solution space, it is rarely really a top-down view, nor is it just a bottom-up view. I mentioned already that's always a back and forth, and this is really important to understand. And this is what is captured in this dashed line. So typically, working in requirements engineering demands for a very symbiotic relationship between requirements engineering and design. What we mean by that is that problem statements and problem solving, so problem stating and requirements engineering and design decisions go hand by hand. And it's always something very, very iterative. And if you think back on the definition of requirements engineering, this is the reason why we wrote iterative into this definition, which means that with every problem statement that I make, so with every requirement that I formulate, I restrict automatically the solution space. I just discard any possible solution that does not really fulfill this requirement. But also the other way around. With every design decision I take, I exclude potential other requirements. Think again of the example of security and accessibility. If I have for example, high demands on the accessibility that people with, for example, visual impairments have to be able to use the system. This restricts already the solution space dramatically to some extent. So this is always a back and forth and back and forth. Anything different than that is an illusion. At the same time, there is still this view on this waterfall way of working. And this is what you can see in the bold line, in the solid line. Where I would first elaborate my context specification, so the stakeholders, the goals, the surrounding external systems, then my requirement specification, and then at some point I'm done. So I take my requirement specification, I throw them to the engineers, and they should just implement this. This is not possible because I miss many options also for my requirements, and it's really impossible to ensure that the requirements are free of conflicts, that the requirements are really feasible, and so on and so forth. At the same time, and this is the last remark, at the same time, there are still situations out there where I need to work, at least to some extent, in a waterfall process model. And this is really regardless of any philosophy that I have with my process. I can develop my software system in an agile manner, and still the requirement specification has to be done and elaborated up front. One example are public tendering processes or multi-stage bidding procedures, where I am a customer, or for example, think of the situation where you are working for an IT department that does not develop software systems themselves, but who contract other software developers to develop these systems. In this case, I typically tend to write a requirement specification, at least in the first version. And I use this requirement specification to get some bids and some solution proposals by those developers. Of course, in subsequent stages, these requirement specifications need to be further refined and revised, but still. But even if I do this, I still, when working on the requirements specification, tend to think of certain solutions. Okay, I tend to put my hands into the solution space and think about how this could be done. Anything else would be highly complicated. Good. Now, let's put all these different puzzle pieces together and think again about the problem space and the solution space. Now, what you can see on the right side are, again, the different levels of abstraction. We have what we call the context layer. This reflects anything that I specify when answering my why question. I have my what we call requirements layer, anything that I specify to answer my what question. Both together are seen as what we call the problem space, and both together specify properties of a system considering a black box view on the system. On the bottom of this picture, I see anything related to this specification of my system layer, where I take a glass box view on the software system. Now, the second thing is I've added some small pictograms, symbolize what I specify. So I can specify my stakeholders, their desires, intentions, their needs. I specify or identify my external systems, specify all the information relevant to understand how I might interact with these software systems. I can specify my domain model, for example, by specifying business processes. Business processes define as principal ways of working in an organization without putting any focus on how these selected tasks and activities should be system supported. I can take this, however, as a basis to identify which function requirements I want to specify. So I can identify which of the single tasks and steps in a business process I want to be, for example, here automatized. So which of these things should be realized by a software system, which should be realized by an end user, how do these things interact with each other. This is just a use case model. Okay, this is just an activity diagram. There are many, many ways of specifying this. But in the very end, what I do is I elaborate what we call as is state to infer all the needs in a picture of the to be state, or the future state that I want to achieve. And to this end, I do one thing that we call scoping. So I define the scope, I define the borders of the system, analyze my functional requirements, analyze my quality requirements, and then iteratively develop my system specification before, again, back and forth, jumping back, refining, jumping back, refining. This is what we tend to do. So the key takeaway is that requirements engineering is never really done unless we have a system specification and can put this really against each other. Now, what you can see here, symbolizing a more artifact-centric view on the core results of requirements engineering. This is exactly what is reflected by the MDIA model, which we will get to know in the next lecture. We have 3 artifacts in MDIA. One is the context specification, capturing the context layer, the why question. One is the requirement specification, and another one is the system specification. Already now, a word of caution, we will not focus, of course, in this course on the system specification. This is not in scope of requirements engineering, nevertheless captured for reasons of completeness. And this reference model we will be using, we will introduce in the next lecture, but keep now already in mind that this will serve as the backbone for the remainder of this lecture. We will be talking about how to create these single content items. So for example, stakeholder models, goals and objectives, domain models, and so on and so forth, moving down to the specification of functional requirements, non-functional requirements, and so on and so forth. Now, with this, I would like To conclude this introduction into the very fundamentals in the extended slide set, which you can find in Canvas, you will find some further do's and don'ts, some more practical recommendations. Most of these things I have said already, but also these parts are more subject to the project Q&A sessions, where we talk really about the actual doing and the specifications. Now, I would like to conclude today's lecture finally with some more discussions on challenges and practices. So now, I would like to start again with a short example. On the left side, you can see an excerpt from one academia industry collaboration that we did. This requirement, and what you can see is exactly as we have found it. And this was a requirement specification that had been accepted, formally accepted, and that was a part of the software development lifecycle. So you can see that it has a small ID on the left side. It has a classification. It was classified as a non-functional requirement, in this case performance, and the requirement itself said the perceived response time shall not be too high. Now, again, I would like you to think what class of requirement this is. Is it a functional requirement? Is it a system-specific quality requirement? Is it a process requirement, considering both restrictions on the development process or constraints, more technical constraints? Or is it neither of the options? Now, for this, we have created a small poll, which I'm launching now. So you can see all these options, and I would like you all to ask you all to please fill in the options as you see fit. The quality requirement, a process requirement, a functional requirement, or is it neither of the options? So the winner is, and the loser is, in fact, it's neither of the options. It's a quality goal. So, and this was a little bit tricky. It's a quality goal, but again, think always of the question, am I unambiguously able and objectively able to decide when I have a software system if this requirement is met or not? In this case, again, the requirement is not really verifiable. This goes far more in the direction than when we had the example earlier about the system shall be secure. This example goes far more in the direction of a quality requirement. So this is true. And this was handled as a quality requirement. This was classified as a requirement, as a quality requirement. So in a way, you are, of course, correct. At the same time, from the perspective we take, especially on these elementary quality properties of single requirements, it's still not really unambiguously classified as a quality requirement. So also the answer, neither of the options is correct. Okay. So let me move on. Oops, sorry. Let me move on to the next. We stay with the very same example. I don't want to refine this now further. We will be doing this also during the exercises, of course, and during your project. But keep in mind that this is from a real-life project, and that the engineers have been working with this requirement exactly as it has been formulated as a quality requirement. Think about what could the challenges be when documenting and keeping the requirement exactly as it has been documented. So what could the challenges be? What do you think? Exactly. We wouldn't really have a goal to go for. This is not really justified. There's no rationale. It's just maybe an assumption. You don't have a specific, this is, also multifaceted. You don't really have a target frame. You don't really have an error margin. So what really does mean not too high? It's very, very subjective. It's not objective. So everyone reading this requirement might interpret it very differently. You as an architect could interpret this requirement very differently to the customer. it's not testable. Now let's change roles to the one of a software tester. You don't really know what values to assign to the test case, what expectations should be, what does it mean too high. But there are also many other challenges related to the management of the requirement. So there is no traceability. You don't really know to which other requirements this requirement might be relating. You have no idea what the priority is. Think of the example we discussed in the first lecture of toll collect, where they were stripping and removing some requirements to meet the time box. So the priority is one important input for that. This is missing. We don't have any context dependencies for example, conflict resolutions and so on and so forth. There's a multitude of challenges, most of which, however, still depend or come from the vague specification of the requirement. Now, let's conclude the discussion with the last question. As I said, this is an example from a real-life project. And by all means, these people are no idiots. They are good, excellent engineers, and still they had this requirement in their requirement specification. Now, what do you think could the reason be for something like this? So what could the cause be for a company, for a mature company, to specify a requirement in this very form? Again, there are many, many possible reasons. But what can you imagine could the reason be for this? Yeah, this is exactly this is what's happened in that particular project. This was a more for political reasons, so they could not agree on a specific response time. At the same time, the customer-contractor relationship was very good. So they knew each other for many, many years. And the developers decided, okay, let's keep the requirement as is and fix it later, at a later stage of the development project. But it was, in this case, it was not really possible to put a number on this requirement exactly. Now, as I said, there are many, many reasons for that, for why requirements are insufficiently refined, insufficiently specified, not measurable, not specified, not objectively specified. One of the reasons is very often, at least, missing awareness. This was not the case here, as I said, is the missing awareness. So many people might not know how to do it better. And even if they knew how to do it better, they might not have the possibilities to do it better, for example, because of time pressure, for example, because of lack of resources. As I said in the first lecture, quite often the responsibilities of doing requirements engineering is shifted to other roles, for example, to the role of a developer or a data scientist or a project manager. They don't have very often the resources to do so, and those roles who are then eventually responsible for requirements engineering don't have the proper training and don't have the proper skills to do so. And of course, there will always be also a certain prejudice towards requirements engineering. Also think about the misconceptions I introduced in the first lecture. Our customer doesn't pay to talk about problems, but to get solutions. Sometimes requirements are just specified quickly, dirty, and then let's start coding. Another thing is, even if you have a reference process model, even if you have a proper understanding about how requirements should be done, and even if this is captured in a specific approach, there could be still the case that there is a reluctance to organizational change, so that people are not willing to follow these guidelines. This is resembled by this exemplary quote: "We have always done it like this." This is something that you will hear very often in the future also, where you just are confronted with another way of working that is historically grown, and nobody really judges about whether it's good or bad, but it's just as it is. So very often they just do it as it is and as they are used to, without putting too much care or thoughts into whether this is good or not. Another thing is, of course, politics. And this is what happened here. They were not really able to agree. At the same time, they were assessing the risks related to this requirement. They said, okay, we have a very We have a very trustful relationship with our customers. So we are used to be working with those customers and we are doing very fine typically. So let's move on and leave the requirement as it is. Missing requirements engineering governance. We have spoken in the last lecture about this quite often. In practice, we don't have clear roles and responsibilities responsible for the establishment of a requirements engineering approach to be used in different projects. And for the improvement of these approaches. Quite often when you go to different companies, you will be confronted with requirements engineering approaches that are historically grown and that are still characterized by software process models that are not in use anymore for a decade. Many of them come, for example, from the rational unified process. Does anyone know what the rational unified process is? It's still out there. It's still being used in one form or the other, but also here, to a certain extent, we have moved on. And at the same time, requirements engineering approaches are still heavily characterized by these, I don't want to say old, but these reference process models or software process models that have been further improved over the years. So in the very end, it's also up to you participating in this course to change that situation, to add new fresh wind, to add new fresh perspectives, for example, by adoptions of these MDIA models. So the biggest challenge still remains and will always be that there is no one-size-fits-all approach that we can use out of the box for requirements engineering. And this is the reason why we will be using a rather customizable, flexible requirements engineering approach. In this case, the MDIA model, the artifact model for domain independent requirements engineering. Just the last word of warning or caution, how to customize that model, how to use it for the projects is not in scope of this lecture, but is in scope of the project Q&A sessions, where end of the next lectures, we will be adopting it step by step towards the needs that you might face in the project. Now, what you can see here is just a small further reading in the slides, and the extended slide set, you will find 2 indicators to some manuscripts. Of course, you don't have to read these manuscripts. These are more academic manuscripts, very thick and putting lots of focus on methodological aspects and so on and so forth. But you can see in the slides a little bit more of a recapitulation of typical challenges in practice. Now, with this, we are coming to an end. I thank you very much for your attention, and it's as always time for questions and discussion. Do you have any questions left? If not, you are more than cordially welcome to join us in the next project Q&A session. Use this session, please, always, whenever you have questions, just drop by, ask those questions, and we can discuss them in more detail. Then, thank you very much. Take care, everyone, and I'm seeing you in the next lecture.